Hello everyone, this is Riley, and today I want to show you the pigeonhole principle and a problem that uses pigeonhole principle to solve that's related to poor English. I'll explain that later. So let's start by defining the pigeonhole principle. In a more formal and general sense, it says if n objects are placed in R boxes, where R is greater than n, then at least one of the boxes contains more than one object. So this is very intuitive, and I can show you by an example that it's also very self-explanatory. It still needs proof, and the proof is quite easy using contrapositive. So let's say if these are the 4 pigeonholes that we have, and we have 5 pigeons, 5 pigeons. So let's draw 5 pigeons in these holes. 1, whoa, that's a pigeon. 2, that's a wing, by the way. 3, that's a big one. 4. Okay, 5. Number 5 has to go into one of these holes. Let's see. Let's say it's gonna be in this one, the last one. So there are 5 pigeons in 4 holes, and so the theorem just says there has to be at least one hole that has more than one pigeon. So it's very intuitive, and the crucial points in using pigeonhole principle to solve the problem is to set up boxes or set up pigeonholes that objects can be in, and then prove that there are more objects than boxes. So that's the main strategy that you need to use to solve a problem using the pigeonhole principle. And now let's jump into the problem. So this is a problem. It states, given any 101 integers from the set 1 to 200, at least one of these numbers will divide another. So basically saying that if you pick any combinations of numbers that's 101 numbers from less than 200, in those 101 numbers, you'll find a pair that divides each other. And by dividing each other, it means that, for example, 3 divides 15 because 15 over 3 is 5 and it's an integer. And 3 doesn't divide 5 because 5 over 3 is not an integer. So that's basically what it means. When one divide another, it has to be an integer, and that's what it means to divide another. And so I actually got this problem from this book, Proofs. The introduction for this problem is very interesting. It says that it's actually Paul Erdős, one of the greatest mathematicians in the 20th century, his favorite problem to give to young and promising children, math geniuses. So quoting the book, it says, Paul Erdős, he also liked to share math with others and liked giving problems to young and promising kids who are aspiring mathematicians. The following was his favorite problem to give. So given that Paul Erdős is a master in combinatorics himself, it's reasonable that he would give this kind of introductory combinatorics problem to the young and promising mathematicians. So I encourage you to think about this problem before you come back for the solution. So let's jump into our solution. When I first look at this problem, I think, why does it have to be 101 integers, not 100 integers? So let's try to think why 100 integers wouldn't work. Like, if you only pick 100 integers, why will there be cases that none would divide another? And the easiest thing you can think of is from 101 to 200. So in this set, it has 100 integers in it, and it's in the set. But none divides another because none of them are twice as much as another. So you have to at least have 101 integers, which makes this set 100 to 200, so that it can divide one another. For example, 100 divides 200 because 200 is twice as much as 100. So we now know that in the set there has to be an n, and there has to be a 2n for the set to have something that divides another. And so in each boxes, then we can set that there has to be an n and there has to be a 2n, because then if you understand the logic, that because then each box, if you have 2 things in the box, then those 2 things are guaranteed to be divisors of each other. So what is the first criteria of the box is that there's one number n and there's one number 2n. That has to be the criteria of the box. So now we think about something else. Think about how to set up boxes and how to set up 100 pigeonholes, 100 boxes. So if we have to think about, oh, let's have 1 and 2 and 3 or some arbitrary numbers to be boxes, that would be kind of a hazard. So let's think about what's intrinsic about numbers in this 1 to 200. So there's obviously there's 100, exactly 100 even numbers and 100 odd numbers. So in those 100 even numbers and 100 odd numbers, we can set each boxes in using that information. So we can use all 100 even numbers under 200 would be a box, would be of its own box. But that wouldn't work because all the even numbers multiplied by any other numbers will still be even numbers. So that wouldn't ever include any odd numbers. So how about let's set up the boxes and so that each box is an odd number. So if each box is an odd number, okay, each box is an odd number. And in those boxes, it will have multiples of 2 of the number. So let's set an example. So for example, there's the first box here, number 1. And then there's the second box, number 2, number 3 actually, because it's odd numbers. And number 5, and so on. So in the first box, there will be 1. There will also be 2, because 1 times 2 is 2. There will also be 4. And there will be 8, and there will be 16, and so on. The first box is actually a very big box. And number 3 would contain 3. It will contain 6. And it will contain 12. And I hope you get the gist of it. So number 5, it will contain 10, it will contain 15, and so on and so on. And when all these numbers are listed out, 100. These will be all the 100 even numbers will be 100 boxes. If there are 101 integers, and you have to put a number in one of these boxes, and when you put when 2 numbers are in one box, they're guaranteed to have a pair that would divide another. For example, any of these numbers divide another, okay? Like 3 divides 12, 3 divides 6, 5 divides 10, so 5 divides 15, so on. So that is what we're trying to establish. So in a more formal sense, say we can assume that if the integer is n, then place it in the box m if n equals to 2k times m for some k. So put it in a more general sense. If the integer is n, then place it in the box m if n equals to 2k, 2 to the k times m, where m is an odd number for some k. So so you can explain this. This is the criteria for the box. So for every box m, you put all the numbers that within this form that n. Just so for example, 72 is equal to 2 to the third times 9. So 72 will go into the box 9. And so on for each boxes. And this would be a criteria of the box. And there are guaranteed 100 box, and if there are 101 integers by the pigeonhole principle, there will at least be 2 numbers who are in the same box, and those 2 numbers will divide another. And this is, I guess, an oral proof / solution to this problem. And thank you for watching. See you next week or later. Bye bye.